All right, what's going on, everybody? Today we are going to be covering the accept-reject algorithm, and what we'd like to do is cover the theory behind it, the intuition, we'll prove the results, and then we'll move over to Python and do a simulation. Now, the theory behind this algorithm is that if you have a random variable y, and its density is described by f of y, further, if there is some h of x that is close to f of y, such that there exists a positive real number m such that this condition holds, so f of y is less than or equal to m times h of y for all y, then we can obtain samples of f of y using h of x. Now, there are a few things to note. The case in which you would need to use this is that, f of y is, let's say that it's really hard to sample from, and there's some h of x that is very well known, easy to sample from, and it's defined over the same values as f of y. So in other words, f of y and h of x have the same support. If all of these are true, then we can go ahead and use this accept-reject algorithm. Now I'm going to go ahead and paste a visual, and let's say that f of y, the distribution in which we are interested in sampling from, is triangular, defined from A to B. And for h of x, we're actually just going to use a uniform distribution defined from A to B. So we're just going to draw a box over f of y. And, well, that doesn't look good. I'll just redo it. We're drawing a box over f of y. And m, remember this positive real number m is going to ensure that f of y is less than or equal to m times h of y for all y. And you can see this in the graph. You can see that our h of x covers f of y. It's a box over the whole distribution. And the way that we would find m, we're actually just going to estimate it using code. You can also use calculus. But we're just going to iterate over a bunch of values from a to b and take the maximum value that f of y takes on. And that'll be our estimate of m. If you iterate over enough values, which shouldn't take more than a second or two using code, you'll pretty much get the exact value. Now, what we're going to do is we're going to generate x-z pairs and determine if that point lies under f of y. Before we investigate the intuition behind it, the algorithm itself consists of two steps. The first step is we're going to take a uniform draw, we'll call that random variable x, from A to B. We will also draw uniformly from 0 to m independently. And if z sub I is less than, if z sub I is less than f of x sub I, we will accept xi as a sample from f of y. Otherwise, we will reject. Otherwise, we will reject and return to step one. And the idea is you will keep doing this in a loop until you have your desired sample size. Now, if we actually look at the graph and investigate the intuition behind this, let's say that your pair is a point that lies right over here. This clearly doesn't lie under our f of y, which is this triangle. Now, if this is our point, then for z sub I, this would be our z sub I, right? It's generated uniformly from 0 to m. And our x sub I is going to be this point over here, which means that f of xi is going to be right over here. And you can see that this condition over here, this criteria, is not met. We can see that z sub I is greater than f of x sub I, and clearly the point doesn't lie under our curve. Now, let's say that instead you were to simulate a pair that is this point over here. Well, in this case, z sub, let's call it z sub j for this case. Z sub j is over here. X sub j is going to be this point, and its height is going to be about yay high. So this will be our f of x sub j. And you can see that in this case, z sub j is less than f of x sub j, and therefore it lies under our curve, and we can accept it as a sample. So that's the intuition behind it if you enjoy thinking about it that way. Now, if you enjoy more of a rigorous approach, we're going to go ahead and prove this result. And essentially what we want to show is that the probability that y is less than or equal to a particular value is equal to the CDF of y. If we can show that, then we have proven the result. Now, if we start with the probability that y is less than or equal to little y, or less than or equal to a particular value, then this is the same thing as the probability that x is less than or equal to little y, given that you accepted the sample. So in other words, given that this x is actually a point, a sample point from f of y. Now, to accept the sample, the criteria is that z is less than f of x. And if we use the basic rules of conditional probability, this is going to be the probability that x is less than or equal to little y and z is less than f of x divided by the probability that z is less than f of x. So we'll just need to set up some integrals to go ahead and expand this. Our first integral for x being less than or equal to little y, well, this is going to be the integral from a to little y. Remember, x is uniformly distributed from a to b, but we would like it to be less than little y, so we'll integrate from a to little y. And for the second part, that's going to be z goes from 0 to m. So we'll have the integral from 0 to f of x. The density for z is going to be 1 over m dz. And for x, well, it's defined from a to b uniformly, so the density will be 1 over b minus a. And then we'll have our dx. Now for the denominator, we'll still need two integrals because z and x are both random variables. So if we actually let x go from a to b, if we allow it to be whatever it wants, then for this inequality to hold, z will need to be bounded by f of x. So we'll actually integrate from 0 to f of x. We'll still have 1 over m dz, and we'll have 1 over b minus a dx. And what you'll note is that we have 1 over b minus a, those are constants, so we can actually cancel them. 1 over m, those can cancel, also constants. And what you'll end up with in the numerator is the integral from a to y, f of x dx. And in the denominator, we'll have the integral from a to b, f of x dx. And when you integrate over the entire domain, you should get 1. That's pretty much an assumption of a probability density function, or a requirement for a probability density function. If you integrate over the entire domain, you get 1. In other words, probabilities must sum to 1, and you are left with the integral from a to y of f of x dx, which is exactly the CDF of y, which is the desired CDF that we were looking for, and thus this will prove the theorem. This is the result that we are after. Right, now we are ready to simulate samples from f of y using this accept reject algorithm. So I already went ahead and imported the packages that we'll need. We'll need NumPy, PyPlot, and Seaborn. I also defined f of y for us, so it will be equal to x over 4 for values of x between 0 and 2. It'll be equal to 1 minus x over 4 for values of x that are between 2 and 4, and then it'll be 0 elsewhere. We also have a plot of f of y. As you can see, it's defined between 0 and 4. It's triangular. And now that we have all of this, we can go ahead and run the algorithms. The first variable that we'll need to think about is what is our desired sample size? How many samples would we like to obtain from f of y? And for now, we're just going to set that to 5,000 to start. And the next thing that we'll need to do is find the value of m. Remember that m is the maximum value that f of y takes on. And because we already calculated all of these y values, we can actually just take the maximum value of that list, and that corresponds to m. The next thing that we'll do is initialize an empty list to keep all of our samples in that meet the acceptance criteria. And we will also keep track of the number of tries it takes us to get to this desired sample size. Remember, not through every iteration, not every sample will be accepted. It needs to agree with our acceptance criteria. So while the length of samples is less than the desired sample size, we will draw from the uniform distribution. We will take a uniform draw from 0 to m, and then we will get another uniform draw, this time from 0 to 4. And if z sub I is less than f of x sub I, if that's true, then we will append x sub I as a sample and accept it. Otherwise, we'll reject it. So we don't really need anything. We don't really need to add an else statement there. It'll just keep looping over and over again. Now, after all of this, what we'll do is we will plot a histogram of the samples. We'll set the kernel density to true, and we'll make the color green. We'll do a grid. Let's do a dark grid, and we'll do plt.show. And actually, one thing that we forgot to do here is add 1 to the number of tries through every iteration. So at the end, what we'll do is we'll print efficiency, which will be equal to the desired sample size divided by the number of tries that it took us. And now we can go ahead and run this. Now what you'll note is that we are actually uh, sampling from f of y. As you can see, it's starting to take that triangular shape. And the efficiency is equal to 50%, which means that it takes, on average, 2 iterations for us to get a single sample from f of y. This is not great efficiency. That can be improved by um, using an h of x that is closer in shape to f of y. We're just using the uniform, which is clearly not as efficient as it should be, or as it could be, if we were to choose a different h of x, but maybe you'd have a better luck or better efficiency sampling from a normal distribution. Now, one thing that you'll note, that we can note, is if we increase our sample size to, say, 500,000, it should still run pretty quickly, and you'll see that it'll really start to take on that triangular shape, and it'll start to look pristine. All right, this is the end of the video. I hope that you all enjoyed it. I hope that you all found it helpful. If you have any comments or feedback, feel free to leave them in the comment section. But other than that, I will see you all next time. Thank you for watching.